This is how a computer writes 0, 1, 2, 3, and 4. But here's a question. How does a computer write -1? You may think it's obvious, and it should just look like this. However, a computer doesn't know what a negative sign is. It only knows 0 and 1, off or on. Instead, a computer writes a -1 like this. Today we're going to be taking a look at why computers typically store -1 as 32 ones, and all of the things that tells us not only about how computers work, but about how our own number system works. To start off, let's focus on how computers write positive numbers. Humans traditionally use the digits 0 through 9 when writing numbers. However, computers are limited by the fact that their wires can only represent two possible values, 0 for off and 1 for on. When we look at typical human numbers, we start with the ones place, then the tens, then the hundreds, then the thousands. The meaning of each of these places can be computed as following. 7 times 1, because we're in the ones place, 2 times 10, because we're in the tens place, 9 times 100, because we're in the hundreds place, and 3 times 1000. When we add up all those values, we get the original value, 3,927. When we look at a binary number, however, the meaning of the places are different. So the first place is still ones, but each place after is actually going to double. So this is the 2's place, 4's place, 8's place, and 16's place. And just like before, we're going to multiply the value at the top by its place. So what does that look like? Well, first we have 1 times 1 plus 0 times 2 plus 0 times 4 plus 1 times 8 plus 1 times 16. 16 plus 8 plus 0 plus 0 plus 1. So that's going to be 25. Another important distinction is that computers deal with fixed length numbers, as opposed to humans, who typically use the minimum number of digits to represent a number. This means that by default, most integers on a computer are 32 bits, even if not all 32 bits are needed to represent the number. A bit is just the term for a digit in binary. So when we write the term 0, it's actually going to be 32 zeros. When we write 1, it's going to be 31 zeros followed by a 1. And when we write 2, it's not just going to be a 1 followed by a 0. It's going to be 30 zeros, then a 1, then a 0. This isn't that different from how humans treat leading zeros. If I wrote the number 009, you would still know that it means 9. This is no different for binary. The reason computers like to stick to these 32-bit numbers is because of the circuitry inside of them. Computers are made of wires, so the numbers they use always have to use the same number of bits as the number of wires on the circuit board. For example, a very common circuit in computers is an adder, which will add two numbers together. When the circuit is designed, it has 3 sets of 32 wires connected to it. The first 2 are for the numbers being added together, and the third is for the sum. Here you can see that an adder would take 3 sets of 32 wires. The first 32 wires would be the first number being added, the second pair of 32 wires would be the second number being added, and then the result would come out of the third set of 32 wires, labeled C in this diagram. You may ask why 32 became the magic size for integers. While I won't go into the full history right now, a simplified version is this. In addition to working with numbers, computers also need to store text. text is stored letter by letter, where each character is stored in a grouping of 8 bits called 1 byte. Since text and numbers share a lot of the same circuitry in a computer, the size of an integer had to be a factor of 8. 16 bits was too small because it could only store numbers as high as 2 to the power of 16 minus 1, or 65,535. On the flip side, 64 bits was often too big, and led to a lot of wasted space. 32 bits was the perfect middle ground. That answers part of our question. -1 is 32 bits because all integers are 32 bits by default. However, that still doesn't explain why it's all ones.
To understand that, we're going to have to take a deep look at the number line in binary.
In a traditional binary counting system, we can calculate the value of 32 ones by adding all of the powers of 2, from 2 to the power of 0 to 2 to the power of 31. This is equal to 2 to the power of 32 minus 1. In computer science, this number line represents what are called unsigned integers, because there is no way to denote if a number is negative or positive. However, computers need a way to store negative numbers too, so computer scientists had to think of a way to denote whether the number you're looking at is positive or negative. One intuitive way that you might do this is to have one of the bits represent the sign of the number. This way we could have the first bit be 0 for a positive number, or 1 for a negative number.
We would continue to use the rest of the bits to convey the value of the number, so from right to left you would still have the 1's place, 2's place, 4's place, and so on. Only the leftmost bit is changing. For example, if you wanted to change this positive 1 here into a negative 1, all you'd have to do is change the first bit from a 0 to a 1.
Let's see what happens to the number line if we changed from the unsigned integer number line to this idea we have of using the first bit to denote the sign. I've marked halfway on the number line here to show that 1 followed by 31 zeros, or 2 to the power of 31, is the middle of the number line.
To show how using a signed bit will change the number line, let's first split the number line in half. All the numbers that start with 0 are on the left side of the number line, and all of the numbers that start with 1 are on the right side.
Since 2 to the power of 31 was originally written as 1 followed by 31 zeros, this is now actually going to be equal to -0, since the 31 bits after the first bit are all 0. On the other hand, 2 to the power of 32 minus 1 is now going to be -2 to the power of 31 minus 1. This is because all of the bits after the first bit are 1. Again, you can compare this by comparing these bits here to these bits here. The only bit that's changed is the signed bit, so one value must be the negative version of another value. There are plenty of benefits to this system. First of all, it's very easy to tell if a number is positive or negative. If it starts with a 0, it's positive, otherwise it's negative. It's also very easy to convert from positive to negative, and vice versa. All you have to do is change the first bit. One of the best things about this system is it's very similar to how humans do it. Even though we don't have a negative sign, the first bit essentially acts as our negative sign, where the 0 acts as a positive sign, and the 1 acts as a negative sign. And lastly, another benefit is that the positive numbers don't change. The representation for any positive number on this number line is going to be the exact same representation that we were using before on our unsigned number line. The only values that have changed are the ones that have changed into negative numbers. However, there are some cons. The first one is that there's 2 zeros, one here and one here. This isn't ideal and can lead to some confusing scenarios. But more importantly, the biggest con that you might have not noticed is that arithmetic is going to behave differently for positive and negative values. For example, previously, both the left half and the right half of the number line were increasing when we were looking at unsigned ends. However, now, the left half is increasing, but the right half is actually decreasing. As we go from this end of the number line to this end, we actually get more negative. This might not seem like a big issue, but it can cause issues with the computer where we now have to redesign our circuitry in order to account for these new negative numbers. Let's see if we can fix these two issues. First, let's address the issue of the right side of the number line decreasing instead of increasing. Let's just try reversing the number line. So what we're going to do is we're going to move -0 to the right side of the number line and -2 to the power of 31 minus 1 to the left side. Now the right side of the number line is also increasing as we go left to right. Fixing the two zeros is pretty easy too. All we have to do is subtract 1 from both the values. So now the left side is just going to be -2 to the power of 31, and the right side is just going to be -1. We've gotten rid of that -0, so now there's only 1 0 left. Now I'm going to rearrange the number line so the lowest value is on the far left and the biggest value is on the far right. This system we just developed is called 2's complement, and it's the default number system all computers use to store negative integers. Let's reevaluate the pros and cons now, looking at 2's complement. I've added this comparison graph so we can compare it to the signed bit system we developed before. We've already gone over the pros and cons of the first system, so I won't reiterate it again. But let's look at this new 2's complement system and see why computer scientists may have picked it over the signed bit notation. The first thing we want to look at is if it's easy to tell the sign of a number. Just like before, all the negative values are going to start with a 1, and all the positive values, including 0, are going to start with 0. It is still easy to tell the sign in 2's complement. It's not as obvious if it's easy to change sign. Let's take a look at how we developed this number system in the first place and see if we can derive a method for changing the sign of numbers. How did we get here? Looking at the right number line, first we just had the unsigned version of the number line. Next, we defined the signed bit, saying that all numbers that start with a 1 must be negative, and that the rest of the bits determine its value. After that, we reversed the number line. And then finally, we subtracted 1 from the value. Looking at it in table form, first we defined the signed bit. For the sake of clarity here, I'm only going to use 8 bits, but all the principles are going to remain the same. The first bit determines the sign, and the rest of the bits determine the value. Here I have -1 through -3 written in binary using the signed notation. All we had to do to get from positive to negative was flip the most significant bit. If we wanted to change these negative values back to positive values, all we'd have to do is change the first bit back to 0. However, that's not where we stopped. Next, we reversed the number line. I'm going to write -1, -2, and -3 again using this reverse number line and see if you can identify what changed for each of these values. You may have noticed that these appear to be mirrors of each other. Let's look at -1. The first bit, 1 and 1, is the same. But after that, all of the bits are different. All of these zeros got turned into 1s, and this 1 here got turned into a 0. The pattern holds for the next two numbers as well, where the first bit is always 1. Negative values always start with 1. But after that, these zeros got turned into a 1. This 1 got turned into a 0. And this 0 into a 1. The same is going to hold true for -3 as well. This is called flipping the bits. So if we combine the first step with the second step, all we had to do to go from positive 1 to negative 1 now is flip all of the bits.
Last, we subtracted negative 1 in order to remove the extra 0. We subtracted 1 from the value that is represented, so the binary that used to represent negative 1 now represents negative 2. The same thing goes for negative 2, where the binary for negative 2 now represents negative 3. However, we don't care how the value changed. We care about how the binary changed. To get this binary for negative 1 into this binary, all you have to do is add 1. This 0 here becomes a 1. The same thing goes for negative 2, where 0, 1 turns into 1, 0. 1 goes to 2. And for negative 3, this 0, 0 turns into 0, 1, 0 turning to 1. So the actual rule that we should be taking away from this is that you need to add 1 to the binary at the end. We now have a process for converting from positive to negative. All we need to do is flip all of the bits, then add 1. Let's visualize this and see if we can find a way to go back from negative to positive while we're at it. First, I want to swap the two ends of the number line so that the flipped bits are directly above each other. Note that this is not actually changing the number line, since both the binary and the values moved with each other. This is just changing how we're viewing it. Let's practice by going from positive 1 to negative 1. So positive 1 will fall right here on the number line. Its value is 1, and its binary is going to be 7 zeros followed by 1, 1. 1, 2, 3, 4, 5, 6, 7, and a 1. The first step we know is always going to be flipping all of the bits. So to flip all the bits, we're going to write the number up here, and it's going to be 1, 1, 1, 1, 1, 1, 1, and a 0. And then lastly, all we have to do is add 1. So I'm going to get rid of that 0 and replace it with a 1. This is the binary for negative 1, which matches what we have written here. Now, how do we get from negative 1 back to positive 1? Well, to start, we know we're going to have to flip the bits at some point, so let's start by doing that. The binary starts as all 1, so flipping the bits is easy. It's just going to go to 0. And once we're at 0, we know that the binary for 1 is just a 1 at the last bit, so all we have to do is add 1. So it turns out that the process for going to positive to negative is the same as the process for going from negative to positive. That makes things easier to keep track of. So overall, swapping signs is a little bit more work than just the signed bit notation, but it's still not too bad, so I'll put a check mark here. However, the next box I cannot put a check mark in. This type of number system is pretty different from what we're used to, so I'm going to put an X here. However, one way we can actually understand this better is by seeing how this number system would apply to a decimal number system. So what if we took the logic of 2's complement and applied it to a decimal number system using the digits 0 through 9 that we're more used to? So to start off, a complement-based number system needs to have a fixed number of digits. So in this case, we're going to limit ourselves to 2 digits, 0 through 99. Just like before, we want to partition this number line in two, where the left half is going to stay positive, but the right half we're going to use to represent the negative values that we want to use. Let's derive this number system using the same process we'd used before. So at the beginning, we said that this midpoint here, 50, is going to represent negative 0, and that 99 is going to represent negative 49. The next thing we did was we swapped the two sides. So negative 0 moves to the right side here, and negative 49 moves to the left side here. Lastly, we wanted to get rid of that negative 0, so we're just going to subtract 1 from both sides. So this becomes negative 50, and this becomes negative 1. You can already see some similarities to 2's complement. In 2's complement, the biggest number, which was 32 ones, ended up representing negative 1. And here it's the same case. 99 is going to represent negative 1. Next, let's rearrange this so the smallest value is on the left side of the number line. Now we can establish some ground rules for how 10's complement works. First of all, if the first digit is 5 or more, the number is negative. In 2's complement, we only had 2 bits, 0 or 1, so it was just a comparison to see if it was 0, positive, 1, negative. However, in 10's complement, we have 10 possible digits, so we have to split the digits into 2 groups of 5, where 0 through 4 is positive and 5 through 9 is negative. Next, the process for converting from positive to negative is going to be the same. You need to flip the digits and add 1. So what does it mean to flip the digit in 10's complement? Well, in 2's complement, we just alternated between 0 and 1. But the really important thing about this flipping of the bits is that if you added the old value and the new value, it'd always equal 1, which is the biggest value. So 0 plus 1 equals 1, and 1 plus 0 equals 1. In 10's complement, we're going to use the exact same principle. So the old digit plus the new digit should always add up to the biggest possible digit, which in this case is 9. So 0 plus 9 is going to be 9. So whenever you flip a 0, it's going to turn to 9. And whenever you flip a 9, it's going to flip to 0. Next, you're going to have 1 plus 8, 2 plus 7, 3 plus 6, and 4 plus 5. So just like before, let's practice flipping positive 1 to negative 1. So positive 1 is going to be right here, and it's just 0, 1. First, you're going to flip the bits, and that's going to change to 98. And then you add 1, and that's going to be 99. 99 matches the value here. So we know that worked correctly as intended. Lastly, here's the real benefit of using a complement notation, is you don't need to use subtraction again. What do I mean by that? Let's take a look at an example. Let's take a look at how we can compute 45 minus 13 using 10's complement. First, we need to convert minus 13 to the 10's complement version. So what's the complement of 1? 8. And what's the complement of 3? That's going to be 6. So now that we flip the 2 bits, all we have to do is add 1. So that's going to turn into 87. And then 45, since it's a positive value, doesn't change. So now we have 45, and we have 87, which represents a negative 13. And adding a negative number is the same thing as subtracting. So we're going to add 87. So 5 plus 7 is going to be 2. Carry the 1. 8 plus 4 plus 1 is going to be 13. 132. But here's the thing. Since we're using a number system that caps out at 99, we actually only use 2-digit numbers. So this 1 is actually extraneous, and we can get rid of it. So the answer is just 32. Let's check our work. What happens if we compute 45 minus 13 the normal way? 5 minus 3, 2. 4 minus 1, 3. These two are equal. Why does this work? Let me show you. Here I have 45 minus 13.
What I'm gonna do next may seem strange, but it'll make sense in a second. I'm gonna rewrite this, but I'm going to add 100 and subtract 100. Next, what I'm gonna do is group these values. So we're gonna have 45 plus 100 minus 13, and then we're gonna subtract 100. And then this we can just evaluate regularly. So it's going to be 45 plus, what's 100 minus 13? 87 minus 100. You may see where this is going already. This 87, this is the tens complement representation of negative 13. 45 plus 87, we already calculated that. That's 132. And then subtract 100. 132 minus 100, that's 32. So this is really all that tens complement is doing. The whole process of quote-unquote flipping the bits is you're really just finding 100 minus x. And that's actually where both 2's complement and 10's complement get their name. The complements, which is the positive representation for a number, and its negative representation, are always going to add up to a power of 10 in 10's complement, or a power of 2 in 2's complement. Both 2's complement and 10's complement just allow us to abstract out the whole process of subtraction by first finding the complementary number and then lastly discarding the extra bit or digit at the end in order to get our final result. So even though it's not similar to humans, there are some clear benefits to this system. Additionally, just like before, the positive numbers never change. We are only manipulating the right side or negative side of the number line. We also fixed 1, 0 by subtracting 1 from the value representation. And lastly, you get consistent arithmetic now. So I already showed you that consistent arithmetic in the tens complement version, but let's end this video by looking at what this looks like in 2's complement. So up at the top here, I have the binary representations of 45 and 13. So first, let's just convert these to binary. 45 is 0, 0, 1, 0, 1, 1, 0, 1. Positive 13 is going to be 0, 0, 0, 0, 1, 1, 0, 1. But we need to flip the bits. So this is going to turn into 1, 1, 1, 1, 0, 0, 1, 0. So lastly, let's just add 1. So we have 1, 1, 1, 1, 0, 0, 1, and then we add 1. So this is a 1 now. And then this we can just bring over. Since it's a positive number, we don't have to flip the bits and add 1. So this is 0, 0, 1, 0, 1, 1, 0, 1. And now let's add these together. Adding in binary is very similar to adding in decimal. In some cases, it's actually easier because there's just less digits to worry about. All you need to know is 0 plus 0 equals 0, 0 plus 1 equals 1, 1 plus 1 equals 2, and sometimes if you have a carry, 1 plus 1 plus 1, that's going to be 3. So let's add these. 1 plus 1, that's going to be 2. Carry the 1. 1 plus 1, 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 2. Carry the 1. 1 plus 1 plus 1. That's going to be 3. Carry the 1. 1 plus 1, 2. Carry the 1. 1 plus 1 is going to be 2. And just like before, we have 9 bits. Our addition system only allows 8 bits.
So we can safely disregard
this last bit. And what value is this going to equal? We have the ones place, 2, 4, 8, 16, and then this is 32. So this is going to be equal to 32, since that's the only bit that's a 1. So that shows how you can use 2's complement in order to, again, perform subtraction without ever actually having to think about subtraction. So this fixes our last problem of consistent arithmetic. So we can add a check there. That's the big benefit of using 2's complement. Since subtraction can be performed using the same logical processes as addition, a computer can use a more efficient circuit. It doesn't matter if a computer is adding 2 positive numbers, 2 negative numbers, or a positive and a negative number. All of the logic is the exact same. Since so much of computing is based off of simple addition and subtraction, making this process as simple as possible means computers will run much more efficiently. So there you go. This is why -1 is equal to 32 ones. Just to recap, how did we get here? Computers need to work with fixed length numbers. So -1 we knew had to be 32 bits long. Computers are more efficient if they require less steps for basic arithmetic. So we can't use a similar system to what humans use, where we just use the first bit to denote the sign and then use the rest of the bits for the value. Instead, we had to be a bit more clever than that. So in order to do that, we invented 2's complement, which allows computers to handle negative numbers without any added logic because, again, 2's complement means we can now incorporate negative numbers into our arithmetic without adding any extra logic. Subtraction is built into 2's complement. That's it for this video. Thanks for watching, and if you liked this video, feel free to give it a like. If you have any comments, drop them in the comment section down below. Have a good day.